It's my pleasure to introduce Eric Fossler-Lucier. He comes to us as an assistant professor from Ohio State, the Ohio State University, as Sanjeev pointed out. He did his PhD at UC Berkeley, and I think the first time I knew about your work was when you were doing your postdoc at ICSE.
Right.
That was when I was most aware of the work. Eric's been doing a lot of work in the computer science department and working with a wide variety of people multidisciplinarily. He has a lot of interest in things like pronunciation modeling on one hand, natural language generation and spoken dialogue systems, multi-stream large vocabulary decoding. I mean, these are really wide-ranging kinds of topics, and yet he brings it all together in a nice package. He's going to present today work that was supported by an NSF career grant that he got in 2006 from IIS
Yes.
when it was under Tanya Korelski.
That's right.
So it was the year after I left. Anyway.
Okay. Thank you very much. So, so I'm going to talk a little bit about the stuff that we're doing in the Career Award. I did want to. I've got like about 5 slides too many. So I want to actually take a quick poll because I'm going to tailor stuff. And by the way, the rules of the game are that you can totally disrupt any talk that I have. We can talk about something completely else. If you want to talk about bicycles, fine. But what I wanted to know is how many people are familiar with basic concepts like phonological feature models and stuff like that? How many? Let me ask the opposite question. How many people don't know about phonological features? Okay, enough that I should do a little bit of background and stuff. Okay, so the way I'm going to try and do this is to give you a little bit of insight as to the kinds of problems that I'm interested in from working in speech recognition. This is just one of the areas that my lab is working in. This is joint work with a lot of various students of mine and actually of another professor in this case, Jeremy Morris, Ilana Heintz, Rohit Prabhavalkar, and Zhaozhang Jin. And what I'm going to talk about is how we're using conditional random fields to do integration of information over time. Okay. So what got me into this was that I did my PhD dissertation in '99, and I did pronunciation modeling, and eventually you do get to realize that everything that you did in your dissertation was wrong. And so the question is, how do we make it right? And the thing that I am very interested in is injecting linguistics into ASR models, okay, that give informative priors, essentially. So we're still doing statistical learning, but the question is, how do we talk about variation? So I'm interested in how do we talk about pronunciation variation. And the reason why everything was wrong is that I was sitting there building models of things where you've got one phone goes to another, okay? And what we need to look at are models which are more along the lines of thinking about subparts of phones and how those change over time. Okay, and that's what a good part of my talk is going to be about, how we're going to use conditional random fields to think about things like integrating phonological features, okay? So I'll give you a little bit of stuff on the timid stuff and some hot off the press stuff that we've done with word recognition. And also I've got a student who's interested in computational auditory scene analysis. So I'll talk a little bit about that. This is not one of my primary areas, but I'm learning, and we actually have a CASA person, Lian Wang, who's actually relatively well known in that field. And so that's why I'm borrowing some of his student stuff to work on. So those are the kinds of things that we're going to talk about today. Okay, so here's a little quiz to get you warmed up, right? You've probably seen these kind of gimmicks before, right? So can you understand the sentence? It takes you a bit to do, but you can remove the vowels, right? And from a sentence and still understand it, okay, right? Or you can change the order of letters in the middle of words and still be able to read it, right? Okay, so we can, it takes us longer to process that sentence, but we still are able to process this stuff, right? And this is because language basically contains redundant cues, okay? And we don't need to necessarily get all the information in the right order at one time, but we actually are processing, we process faster when things are in the right order, but we can still make out the things when there's sort of variation going on. Okay, so here's, now for the speechies in the audience. Here's a little test. Can you figure out what this common phrase is? Raise your hand when you get it. Ooh, it's taking long. It's 4:30, I can tell. Okay, I get one. Jack's got it. Okay, good. That's right. Okay. Senior Research Associate. Right. Okay, there you go. It took a while because there's some variation that goes on in there. Okay. Now, what's really going on here is that the stressed syllables in here are actually modeled with the actual pronunciations, and then we have variation in the unstressed syllables here. Okay. Now, the point I wanted to make with this is that if you looked at the dictionary pronunciation of the words, you get one pronunciation. Now, if you look at what transcribers would write down as a pronunciation, and this was actually something that was in the Buckeye corpus of speech, you'll notice that there is some variation here that occurs. So instead of we get r, sort of an unstressed instead of e, we get I. So research instead, right? And so you can see that there's some variation going on here, right? And so, well, okay, you might say, oh, well, I would learn a model that basically says associate might be associate, right? And learn that kind of variation. Well, all right, fine. But that's sort of a little heavy-handed. And the thing that is really going on is that you've got, there's some pattern to these changes, right? And what's going on are things like, here I've got instead of research, right, I get research, right, where there's a change in the place of articulation, right? These types of phenomena are pretty common, and they happen in spontaneous speech all the time, and in fact, we just gloss over them, right? And yet, they're problematic for speech recognition algorithms because things like this, you now have to have sort of a looser model for s, right? Because you can experience this kind of variation. Okay. So what I'm going to, to get an idea of phonological features, you can think of every sound of a language as having some sort of canonical feature definition, right? So cat might start with a k, which is voiceless. There's a k versus g, right? Velar meaning the closure is in the back, and a stop meaning that you've completely stopped the airflow, right? T is also a stop, but it's got a different place of articulation, right? So we can talk about phones in terms of things like place of articulation, manner of articulation, vowel height. So there's a difference between E and A, okay? There's a difference between E and U, which is front to back. And if you're German, you have a difference between E and Ü, which is lip rounding, right? In English, we have a correlation between these things. Basically, we can think about, one way to think about pronunciation variation is to basically say, well, it's changed from one symbol to another, or another way to think about it is basically you just change one place of articulation. And actually that accounts for more than 90% of the variation that you actually see in things like Buckeye corpus and switchboard and all these other transcribed corpora. Okay, so people have pitched the idea of using phonological features before. There's quite a bit of literature on this. You know, you can do some things with phonological features that are kind of hard to do with phone changes. So, for example, oo, right, can sometimes be fronted, so toot, right? So it's common enough that basically Timmett introduced, which is a phone one of the early phone hand transcribed databases, introduced a new phone, which is fronted oo, right? But that change of symbol actually loses all the commonality between oo and ü, right? So you kind of want something that sort of says, there's a relationship between these two things, and that's what phonological features can give you. Okay. I'm going to skip the rest of these points at the moment and just go on to this. I don't want to say that, so like anything that I'm going to tell you today, nothing is a panacea, right? And so there are problems with phonological features. So for example, if you're talking about high vowels in English and you're talking about high vowels in Japanese, these are not the same vowels. They're not even the same height. And so it's not like these are, you can just say, okay, I can take this set of phonological features and transform it and I will get exactly, the right thing in another language. Okay, so it's a little, they're kind of related, but they're not exactly the same. So one of the other thing is I sort of said, well, you could break down a phone into, multiple independent dimensions, but actually these dimensions are not really truly independent. So one example is in English, we have this correlation between rounding and frontness, backness, right? Okay. So now if you want to sort of measure things along some sort of distance, if you want to measure some sort of phonetic distance between segments, right, you now have to take into account the fact that there is this correlation going on. Okay. Other point, these can be difficult to transcribe. Karen Levescu did a nice little study where they actually did do some transcription of this kind of stuff, but it turned out to be kind of expensive to do. So it's hard to get at the actual underlying like stopness of something or fricativeness of something, right? And part of that it has to do with the fact that there are different definitions of what all these ways of looking at these features, right? These subphonetic features. And so you can think about things in terms of, the way I've described a lot of these features are in terms of what the articulators are doing, right? But you can also think about acoustic features that are things like, I sensed a burst in this area with a particular formant transition, right? And that's a more of an acoustic event, right? And learning the mapping, and there's not a one-to-one mapping, like with the phone problem, there's not a one-to-one mapping between articulatory features and acoustic features. But that said, we're just going to sort of say, well, okay, but they are description, right? And they're useful sort of abstraction, okay, that we're going to use. So how do we get at some of these things? And I want to just bring up a cute little study that was done first here, and then we followed up with a little bit of study of our own, where you take a look at transcription, right? So we get a linguist or a bunch of linguists, sit them down in front of a computer and basically make them transcribe, possibly by giving them some hints about what was said, transcribe the phone string. Okay. There's some bias involved, and you can argue about particular things, but basically we can get some sort of sense of what is going on in terms of the phonetic string, right? About what the transcriber believes is going on. Okay. Now you'll notice that this often differs from the dictionary pronunciation, right? And we tried to play around with this. Various ASR researchers have tried to play around, with using these as seed models for trying to do things like pronunciation modeling, right? You would think that having linguists sit down and transcribe these things would be a really good idea. Just, let's take that as seed knowledge. Maybe we use it as a prior in our model. So Mike Riley did a study here at one of the summer workshops and basically found, you know what, it was better to just ignore that data altogether, right? Why? Excellent question. Why? So here's one. I'm glad you asked that question. Yes. Did I have a plant in the audience? I don't know. Right. Okay. So here's the fine gentleman here in the front row and his fine student did this lovely study where actually they looked at acoustic models where the transcriptions actually differed from the canonical. So the idea is if I had the word cat, but it was transcribed as eh, right? That ah sound was transcribed as an eh, right? I look at that model, right? And they looked at the acoustics of canonical as, and then as mapped to es. Okay, and what you would expect is if the transcribers are looking at particular particular things, you would expect things to kind of look kind of like rather than like in this situation, right? But actually, that the means of things that were transcribed goes to often were sort of halfway between the two and actually often closer to the canonical, right? So it's like, well, this is canonical, but sort of off of the radar a little bit from what a normal thing is. So we did this study where we looked at some data from the Buckeye corpus, and so here's an example from that study. Basically, let's take the situation where it's transcribed as We'll look at 80 vowels from one speaker, right? And we're going to just take a look at, we're going to look at exactly the same situation. As go to as go to as, and as go to as. Okay. Let's look at the formant frequencies from the center of the vowel, okay? Because that should be an indication of sort of where in the space this is. It's a very rough approximation. Okay, so here are my original data. And you can see that there's sort of two groupings. The circles aren't like any statistical thing. It's just sort of like me drawing, right? Just to give you a sense of like, here's ness and here's aness, right? There's data points that are off here to the side, but basically this fits the pattern. Okay, so where do you think if I look at all the things where was transcribed as where do you think it would be? Is it going to be in here? That's where we would hope, right? No. It's all over the place. Yep, sorry?
You're kind of pointing us in what I would think is misleading way. Mm-hmm. Because I think if I would look at the squares, it's just more variance, basically. That's it. I mean, those data have more variance. I mean, those.
It could be.
Yeah,
it could be.
That's really the key.
No, but here, let me show you the point that the data. Yes, you're right. There is more variance, right? But more variance in a particular dimension. Okay. So hang on to that thought. Okay. Basically, right. Okay. So here. We do have some in the mixed to territory. We have some that are above I should say. So they're actually, if the transcriber were being honest, it should have marked it as right? There's actually some things that are lower than right? Well, there is actually nothing that's lower than right? So the transcriber wouldn't be able to mark that as anything. Okay, so we sort of see the data being all up and down the side. Where is the data not?
Here.
Yes?
I'd like to make a point. The thing is that you're imposing people's perceptions on top of these measurements.
Yep.
And there's a lot of individual differences in terms of perception of the space as well. And so people are interpreting based on their perceptions, and that adds another dimension as well.
Yes, that's exactly right. And so the question is, what is their perception telling them? That's what I'm trying to get at.
Well, and there's a lot of individual differences in perception.
Agreed. But hold on, let me just where the thing it's telling is this blank space out here. There is no data out here. Right? That's the key. The data is all up in here. Right. So what it's saying is, I don't know what the height is. And I'm just going to mark it as something is not right? And the thing that I can think of that was not is right? That's sort of the canonical thing for that, right? Why did I choose instead of right? It's because, I'm pretty sure on the frontness, right? I am not sure at all about height. So the point that I'm trying to make here is that some features may be more certain than others. And one of the things that we can gain from transcription is not the actual value of what is actually transcribed, but rather the fact that there's a change in a particular dimension means that we're uncertain about the dimension, right? Now that's not to say that this always works, but it's a rough way of thinking about it. Jack.
So I can't help but ask you, have you sorted out all the bad people, the people who have that alternation? There are no such people here. Like
There
I
should
say
they.
bad,
Yes.
So if you take all the voice context out,
Yeah.
you get a much narrower distribution for people from that.
Yeah. So the way that this was done is, I mean, so we haven't subselected any of the data. I mean, this is whatever the transcribers happen to do. But so there's basically only a couple transcribers involved in this. So the number of people involved for this speaker is actually going to be low, right? So this is actually, like 2 or 3. This is transcribers, right, working on this speaker. So there's only like a couple transcribers working on this. So we're talking about n individuals' perceptions. This is why I don't draw any huge conclusions from this. But the way that the transcribers were selected was that we tried to get them from the Columbus area.
I'm more worried about the speakers than the transcribers.
Well, this is a single speaker,
I see.
right? So I didn't want to even get involved with like vocal tract length or anything like that.
No, it's not
Yeah.
it's not from a
But-
alternation dialect.
No, that's right. That's right. Well, it's from this. Let me see. This is S11. So it turns out that there's a dialect boundary that actually runs right through the middle of Columbus. So I don't remember whether this one was above or below whether this is the Appalachian
I mean, did
or the
you have
Midwest.
the same vowel before voiceless?
I believe so. Yes, that's right. Yeah. I'm not 100% sure on that, but I believe that to be the case. Right. Okay. So my only point for this slide really is we can think about certainty of various things and uncertainty of other things. And so what we want is a model that we can start to think about, hey, I can trust this feature, and I can't trust this feature, right? How am I going to do that? Well, I'm going to maybe try and observe that from data. And that's what the conditional random fields are going to get us. Okay, that's what we're trying to do. Okay, so this is just the same thing I just said, which was, we can't, it doesn't sound like a canonical phone. I don't know what it is, but I know that the frontness is kind of right. Okay. Okay, so, all right, so now the question is, let's move more from the linguistic domain into the engineering domain, right? How might we go about trying to model this in an ASR system? So what we'll do is we'll take some set of phonological features and we'll train them, and because we'll do the expedient but wrong thing of basically saying, I have a phone level transcription. I'm going to convert that phone level transcription into a phonological feature transcription. That's wrong. It's not the right thing to do because there's still some phonological effects. But at the moment, it's the best we can do, okay, as a first thing. But the idea is what we're going to do is train one system that says, this is going to predict the manner of articulation. And hopefully what we'll do is if we see enough of these examples that we'll learn when the manner is actually wrong. The system will still predict the manner in a non-canonical way, right? Sometimes it'll predict it the canonical way because that's the way we trained it. But if it's sort of a blatant violation of stopness versus fricativeness, right? Let's say, then it might change its mind about manner. Okay. So a lot of this stuff, and I'm using some detectors of all of these things based on usually things like multi-layer perceptrons or time-delay neural networks or stuff like that. And we have an SF grant with Georgia Tech and Rutgers in which we're doing this automatic speech attribute transcription project where people are focusing on different ways of building these things. Okay. Now there's a number of other phonetic events that you might talk about, like phones we actually use instead of talking about the phonological features, right? If you're of the Mark Hasegawa, Johnson, CLSP Wilson sort of frame of mind, you might do landmarks, you might do burst detection. If you're Keith Johnson, various things you can imagine doing, right? All of these are events in a speech stream, okay? And the question is, given a set of events, how do we combine them into phone estimates? Okay. So what we're going to do is have a sort of a traditional neural network system for our baseline system, where we're taking an MLP, a multi-layer perceptron, and predicting, given some acoustic range, what is the probability of some event, whether it be a phone, a phonological feature, whatever. Okay. And then we're going to combine that evidence using conditional random fields. So CRFs, basically, if you've ever seen maxent, it's basically maxent with the ability to talk about neighbors, right, and have influence of neighbors. Okay. And so therefore, it's a log linear model. So you can, one way of thinking about it is it's kind of like a single layer perceptron. It's sort of like the top layer of a multi-layer perceptron. So one way of visualizing all this is that we're putting another layer on top of a multi-layer perceptron. Okay. Okay. So, so what, people are starting to do this a little bit with it, as an alternative to HMMs. And the question is, well, what do you get out of that? Well, one is that CRFs are usually trained using a discriminative training criterion, which you can do also with an HMM. Okay, I'm not saying that's right. But what we're going to do is directly estimate the probability of some label sequence given the acoustics. So here's my label sequence, and I want a probability over the sequence, not just over each individual label, but over the sequence given this input. Okay, the input features can be arbitrarily defined and can be overlapping. So actually, this representation of the cloud basically is to say, hey, you can look anywhere in the X you want. Okay. Now we can also make these transition functions depend on the evidence, which is something that you can't do in a straight up HMM. You can do it in other ways with dynamic Bayesian networks and stuff like that. So again, don't take it like gospel, like this is the way to do these things, right? This is just, these are convenient things that you get for free. Now, what we're going to do is basically, I'm going to restrict myself to thinking about the more time-aligned type structures that you might see in a standard HMM for the purposes of this talk. Okay. Now you can imagine doing things like cross-dependence of things, and we've done this kind of experiment. None of the experiments that I'm going to talk about today will have integrated that. Okay. So we'll leave those out for the moment. Okay. Now, but what we are going to do is that we're not going to directly talk about these x's, but the name of the game really is finding functions of the input that you can use to describe relationships between between the data and the labels. Okay, and there's a number of different games that you could play with this, and this is actually where all the smarts have to come in, right? So you could use the sufficient statistics of a Gaussian, basically take the features, they're squares, and you could use them, and you can actually model a single Gaussian system using this type of thing. Okay, and that's what modulo a hidden variable that's in here. That's what the Microsoft guys had done. Okay, you can imagine there's work in Steve Reynolds' group, Yasser Hifni, who's also Abdel Halim, had these Gaussian affinity functions, which is essentially how far are you from a particular. So train a system, you get a bunch of Gaussians. How far am I from each one of these Gaussians? Right. Take the top n, and that's a representation of how close you are to things. Okay. Ilana Heintz did a bunch of things, taking the stuff that I'm going to talk about and generating new features by basically looking at a single value decomposition of different feature streams. Okay, but the thing I'm going to focus most on today is basically using these MLP posteriors directly as inputs. Okay. Yes, sure.
The way you write it, you write your observations as simply f of x4 or f of x5.
Yeah.
If I remember, maybe I'm remembering wrong, actually your f would be f of, for example, x3, x4, x5, right? It doesn't have to be f of only x4.
It could, right, exactly. It could be a general f of x.
Right, it's
yes.
some general function of the,
that's right.
and speech input.
So in general, you have some function over, you can make a deficient version of this where you leave off this, right? Actually, let me go one slide ahead. Okay. So here, I could talk about the relationships of a state to all of the input, and then I index it by time, so then that would be, so I could look at a window like that.
Right.
That's right.
So
Yes,
that
exactly.
F could be a function of
F
a
could
chunk
be,
of speech.
right, it's an arbitrary function in this case, right? So in fact, with our, when we have a multivariate perceptron, X is actually a context window of 9, because when we, in the traditional way of doing these MLP estimates. Okay, so so what you're doing is you want this global, this is a probability over the entire Q sequence given X, right? Which is basically the maxent, I mean, this is basically a maxent style thing where you've introduced this additional T, which sums over the time, right? Lambda weights times these feature functions. So essentially you're doing logistic regression in, you know, over these functions and trying to learn the associations to from that to label sequences, okay? And of course you have the Z of X term to try and normalize everything correctly. So let me see where I am in time. Okay. All right, and the only point that I want to make here is that you can split apart things into state functions and transition functions. And just to point out, you can have dependence on the X for the transition function as well, right? So in an HMM, you would drop these things. And in fact, we often add bias terms where we drop the X, and we just basically say, did I observe this state? Did I observe this transition, right? So you can talk about any sort of, you can ignore any one of those inputs you want, essentially. Okay. So here, these state functions are going to be attached to particular states, and the transition functions are going to be attached to the particular transitions. Okay. So our job now as a modeler is to basically pick S and T functions, and this is where our MLP estimates of things like phone posteriors and phonological feature posteriors come in. So I replace this, right, or I use as one of my functions, for example, what's the probability at a particular time that I saw a T, right, according to my MLP? Or what's the probability at a particular point in time that I saw a stop consonant, okay? Now, if I put both of those things in the system, right, these are correlated features, so the CRF needs to learn how to balance out the fact that it's going to get multiple pieces of evidence thinking about the same thing, okay? So the model's job is basically, given a particular feature set, find the appropriate lambda values, right? And that the way that it's typically trained is using what's called the conditional maximum likelihood, right? Where you're maximizing this conditional probability. Now, if you know maximum likelihood tries to maximize this likelihood. This is the likelihood of the labels given the acoustics, I guess is the right way to phrase that. And how does that work? Well, basically, we're going to do gradient ascent, and you can do essentially the same thing you would do in an HMM, which is to collect alpha and beta statistics and get occupancy, and essentially you want to make the expected value of the features equal the actual observed values of the features, and if you've done maxent, it's the same story. And you can go walking up that gradient in any one of a number of ways. So you could do iterative scaling variance, you could do LGBFS, you could do, what we do is stochastic gradient ascent. We find that this actually converges pretty fast for our problem. May not converge fast for other problems, right? So the nice thing about this is that if you take a look at, say, like the ICSI QuickNet package, this is exactly the same algorithm that's in there. Okay, so it's very much in the same flavor as MLP training. Okay, all right, okay. So let me give you some initial experiments as to like what happens if you start sticking these MLP posteriors into CRF system. Okay, so what we're going to do is we're going to start with PLP coefficients as a spectral representation, and then use MLPs to train this. Now, you can use what's known as the tandem trick, which basically takes these MLPs, does some decorrelation, and insert them into HMM, and that's the work of another fine person sitting in the second row, Dr. Hermansky here. So we're going to take that same MLPs, and we can stick them into the CRF as the feature functions. Okay. So one is that you have 61 phone posteriors here. So I'm going to use 105 inputs. One is we're going to take these phone posteriors, and another is going to take 8 classes of phonological features, which total 44 inputs. So essentially, the sum of this is 8, and the sum of this is 1, if you think about it that way. Right? Okay. And you can see that basically it works about the same as the tandem system. This is not a statistically significant difference. This one is significant when you add a little bit of transition features, but I don't want to make any huge claims about this. Basically, you can see that you can get roughly comparable performance out of doing this kind of stuff. Okay. So we took those 2 sets of features and we just stuck them in as features. One of the things I wanted to say, this is sort of a sidelight, and there's another talk on this, so I'm not going to give you the whole story of this, but basically imagine instead of having 2 of these streams, I might have 6 of them, right? So I can come up with different representations. Like one of them, our friends at AFRL gave us their feature definitions for that data, right? And so we got 6 different representations. It doesn't really matter for the purpose of this what's going on. In terms of the actual streams. The interesting thing was that we found that you could stick all of those into the CRF and it would do a little bit better than you get into the 72s with this. So the previous number was 71 and change, right? So you can get into the 72s. One of the things that we found is that if you take the dimension of if you just reduce the dimension of each stream by doing, well, we originally did these SVD decomposition, but it turns out that basically any dimension reduction will work for this. But then combine those streams with an MLP, get a posterior estimate, and then use that as the features for the CRF, right? This actually gives a significant improvement on Timmett, okay? What does that say? It says that the phonological feature and the phone features and all of these things that we were combining combine in a nonlinear way, right? If I could get it to combine in a linear way, then the CRF should have been able to learn that function appropriately. I needed the assistance of a nonlinear combiner to actually get the information out of the stream. So that's an interesting effect of that. Jason?
When you combine the streams, they're time aligned?
They are time aligned, yes, that's right. That's right. And in fact, we're not, the CRF is only looking at a single window. So you could imagine, we didn't try this, actually that's an interesting question. We didn't try this where we look over a wider window for the CRF. But that would be it. The MLP does take into account that window. Oh, I remember now. Okay, I'm sorry. Yes, now I remember the stories. We did the version where the MLP looks over a window and didn't, and the CRF looks over the window and it didn't. It's nonlinear rather than the window. That's the crucial bit.
So the way I understood this slide is maybe wrong. I thought you were saying that the MLP is going to look at a window around the consonant phone to see whether that phone accorded well with the window, and would also look at the outputs of the posteriors from 6 other systems.
Now, it just looks at the window of the posteriors of the 6 systems, not the actual original data. It doesn't look at the original PLPs.
So it's just a combination of system outputs, but it's looking at a window of several outputs, of a whole
yes, that's right.
3 or more phonemes from each system, and not just
a whole bunch of estimates from all these different streams. That's right.
Yeah.
That's right. And so that was one of the things that we were worried about, is that it was the windowing and not the nonlinearity. But when we did the cross experiments to isolate it, it was the nonlinearity that was really important. Okay.
Another clarification question. I'm
Sure.
trying to get a sense of what these streams of posterior information are. So if you just go back to the previous
Oh yeah, sure.
So I could say that in this system already you have 9 streams. One stream has a 61-dimensional output, and there are 8 other streams with
That's
very
true.
small dimensions.
Yes, that's right.
So I could think of these as 9 streams.
That's true.
And you're saying, why stop at 9? Let's put in a few
Let's
more.
put in a few more. That's right.
Okay.
Yes.
And in this particular case, one of the 9 streams, for example, would be a manner feature, which takes maybe 4 values.
That's right.
And so going forward, you have some other feature stream provided by your Air Force. Is that Air Force?
Yeah, Air Force, yeah, yes,
So
that's right.
they said, okay, we do phones
Yeah.
features of this kind.
So actually, so one of the things that, so what I was using to indicate stream here was this could constitute a complete description of the thing. So if I just took the manner, I wouldn't be able to get a complete description of the phone space, right? So, but you're right in the sense of I am basically just giving, a lot of different kinds of information, and different views of these things. And I could think of these things as individual things. The difference, as long as we're on this topic, what's going on in the AFRL stuff is that they actually were giving us 36 binary log posterior ratios. So they're thinking of, instead of having these 8 classes, they actually treat each feature as a binary yes, no, does, right? And then they give essentially what we're calling the log posterior ratio, which is basically the posterior of the correct class to the posterior of the incorrect class. Right.
So in their case, their features, the ensemble of, you said 38 of them?
36, yeah.
36 of them. So first of all, their ensemble is enough to identify the phoneme.
That's right.
And
That's
secondly, there might even be constraints within it, because if it's going to be one of these 60 phonemes, you can't have certain bit patterns.
That's right. Exactly. Right. The interesting thing is what happens when you get invalid bit patterns, because it's going to happen, right? And so that's one of the things that the CRF we're trying to do in the CRF is sort of recover from errors that you might get because you're getting invalid combinations of bit strings in that scenario. So this is actually just over the Timmett training set. I mean,
It's pretty small.
It's small.
So maybe with more data, we have other conclusions too.
Exactly. And so let me do the following. Let me skip ahead to this point, and then I want to get back to the other I want to get back to your question in a second, because we do actually start to look at Wall Street Journal systems and things get a little hairy. So okay, so one of the questions is, let me go back here actually. This is the point I really want to make. Okay, so here, if you've got a generative HMM model, it's pretty clear that you can pretty much go from a P of the likelihood of the data given the acoustics, add in a pronunciation model and add in a language model, and you can get a likelihood model of this. Well, I'm sorry. You could get P of X given W in a pretty straightforward way, right? I guess is the rate. The problem is that what we're getting off of here is actually P of Q given X, right? And so there's not really a straightforward path to word recognition. So we're sort of following multiple paths and trying to deal with that. One is that well, let me actually, I'll just skip right ahead to the point. Is that what we're going to do is use a CRF and use the forward-backward calculations in the CRF to get local posteriors out that are kind of like MLPs, okay? But they're going to be globally smoothed local posteriors, right? Okay, so we're going to take the CRF system and the tandem system, and we'll get a random system out. And the question that we were trying to look at in this particular study is there a loss of information in using these local posteriors in the HMM relative to the CRF? Okay? So, yes?
What do you mean by local posteriors?
The local posterior, okay, yes. So here, we're going to compute at every time step, what's the probability of Q at that time step? So what's the probability of a local individual frame of Q sub T, right? So for every time frame, I'm going to get over my vocabulary of phones.
But X is still the whole thing.
Yeah, X is still the whole thing.
Okay.
That's right. That's right. So here, instead of having, in an MLP, basically you're looking over a context window, X is essentially over the entire thing, right?
So I understand the second bullet. I don't understand the first maybe bullet.
This one.
Yeah.
Yeah. Okay. So we're going to
Yeah.
so we're going to use so the tandem system. Sorry, this is what I get for putting this out of order. Okay. So here's the work of our fine professor here, right? Hynek and Dan Ellis and Hynek's student basically came up with a system there's a long story behind why they came up with this system, where they basically were taking these MLPs and changing them into feature functions for an HMM, okay? And the problem is that posteriors themselves, if you thought about like making Gaussian distributions over posteriors, those posterior dimensions are going to be correlated, right? So, okay, that's diagonal covariance matrices are going to be really problematic. How do we fix this? Well, one thing you can do is take the log of the multilayer perceptron, and take the log posterior, and then do a principal components analysis on it to decorrelate. Okay. The other thing you can do is, since these are softmax output, it's roughly equivalent, but not quite equivalent to just take the linear outputs off of the hidden layer. And in fact, you can strip back multiple layers of this, and people at ICSI have been playing with this for a while. But the point is that you take it into some sort of log domain, and then do a principal components analysis, and that gets enough decorrelation that you can actually now compute reasonable Gaussian features over these data. Okay, so we're going to play the same game. Yes, yes.
Because I'm still not 100% sure I have it. You're going to take the acoustics, or Hynek's going to take the acoustics,
Yeah.
and replace the MFCCs with features that are extracted in this way. So the acoustics have just been replaced by the system. Is that right?
That's right.
So they are posteriors basically of classes you may want to use in your HMM, but they are quotient-ized and they are decorrelated. So
Yeah.
Or the way Fred would say, this is all part of the signal processing now.
right, this is
Yeah.
Now the action begins.
So it's posterior-oriented signal
And
processing.
the PCA is what's doing the decorrelation.
Yes.
This is feature
Right.
description.
And the input to PCA now is a distribution over passable output cones at that position.
Yeah, I mean, you can think of it that way. The log posterior, but yes, yes.
Okay, something about the dimensionality isn't adding up to me, because that's one dimension, and you need two dimensions as your input to PCA.
No. It's so.
So you do it over all the tokens.
You do it all. So you.
Think of Q as a vector. So
Q is a vector of probability. So basically, for every time step, I have a 61-dimensional vector.
I got it. So that gives you your matrix. You do PCI over everything, so it's
Right.
decorrelated across time.
That's right.
Okay, good.
Yep.
Okay, thanks.
Good.
I appreciate it.
Okay, so basically we can play the same game, and the question is, how do you get that local posterior out? Well, basically, you do alpha beta recurrences to figure out the local occupancy. And this is something that we do during the training anyway, so hey, we got that for free. Okay, so the question is, how do I make this look sort of like the choices that we did for the tandem system? One is to take just the log of that, and then take the PCA of that, right? The other is to basically ignore doing the normalization and take away the exponential, and this is essentially equivalent to the same operation that you do with ignoring the softmax output and just using the linear outputs, okay, in a multi-layer perceptron. Okay, turns out that for the purposes of this talk, they're equivalent. Okay, so we're just going to assume that we're taking a log posterior and doing the decorrelation. Okay. So here was a slightly surprising result. We kind of expected this to do worse than the CRFs, maybe about the same as the tandem, but it actually improved things a little bit. Again, this is not a significant difference here between these two. This is actually significant between these two. We're actually kind of creeping up here from the 70.9, which is kind of nice. So we thought, hey, we're doing great. And then word recognition. Okay, so the whole point of this is that we could actually start doing things like word recognition now, right? And so we did the same. This is sort of hot off the presses. Just went off to interspeech kind of thing. Okay, so we trained for Wall Street Journal. We trained the same sort of system, and we noticed that on the development set, we're improving the phone accuracy, and actually we actually do end up doing a little bit better on the dev set than the tandem system, but on the eval set, we're not generalizing as well. Okay, but the weird thing was this, and this is true on both the dev and the eval set, that as we got better with the phone accuracy, the word accuracy degraded. okay? And this comes back to the whole point of the training criterion, right? We're optimizing the wrong thing when we're training these things, okay? But I also want to point out a little bit of difference that might explain sort of what's going on here in terms of these differences, okay? Interestingly, one of the games that people play with this is they add in the original features, and yeah, okay, you get the same thing, but this is not the important thing. So, one question is, why do you get this? Okay, why was there a slight degradation in this? Okay, and why, and moreover, why do you get even worse? Okay, so here's a trace of the posteriors that come out for an utterance. I think it's on the development set, but it doesn't really matter which. You'll notice that the MLP is pretty peaky. There's a lot of information that's sitting down here in this region. The CRF is very certain about itself, right? And the according to it, incorrect classes are pretty suppressed. And that's not surprising because that's the way that we're trying to train these things, and the smoothing that you get from having looked at what's going on in your neighbors basically allows you to sort of overrun some of these things.
So each color corresponds to one phone class?
Yeah, exactly.
Are they correct, the high ones?
Neither are necessarily correct, right? This one works a little better on this thing. Okay, so you'll notice that these things are kind of, if you imagine trying to think about what these points look like in space, the ones that are up here are basically points at 1, and then every other dimension is 0, right? And even after you do the decorrelation, you're going to end up with things that look very non-Gaussian. Okay, so we think that the Crandom system, the more you train it, the less Gaussian that the distributions actually become. So we think they may not be appropriate for HMM observations, right? Now, we started to do some, and one of the points of the interspeech paper is to sort of investigate what the heck's going on here. And we noticed that, hey, it's more certain of itself even when it's wrong. And now we might actually call for some old-fashioned pronunciation modeling, right? So one of the things that we noticed is that if you looked at the if you do phone recognition over this, right? One of the errors that it made is it misrecognized the word officers. And the reason why is that because the phone recognition thought it was officers instead of officers, which is a totally normal, phone substitution there, right? So, but because the CRF had pushed it farther apart than the MLP, it couldn't recover from that, and basically it got of-isers or something like that. I don't remember exactly what it was, right? Okay. So one of the things that so pronunciation modeling may come back into play now again, right? Or we may need to think about how to smooth, to not make these things as smooth. And so one of the things that we want to do is look at adjusting the training criteria to, instead of maximizing the conditional maximum likelihood, we're going to maximize things like word correctness. Okay. So, that's sort of future work. Okay. So I am pretty much almost out of time, but I should also point out that the other thing that we want to do is build decoders that use the CRF directly rather than plugging them in HMMs. So that's one of my student Jeremy's sort of dissertation projects, is to basically do these things using FSM techniques. Okay. So we do have some preliminary work on TI digits. It seems to work kind of okay. Okay. So I'm just going to touch briefly on this. I have a student who's a relatively new student to me, who was interested in thinking about multidimensional CRFs. And we're eventually trying to target the idea of building systems where we're thinking about phonological features at the same time as phones in a multidimensional way. Okay, but the question is, well, we're not really ready to do that yet. How can we find a problem that we might think about structures that look sort of like that, right? Where I've got essentially, let's say, multiple labels in a two-dimensional grid, and these are attached to some observations. Okay. So luckily, in the lab next door, we have people who are working in CASA, right? And the idea is, if I was going to do my one slide on CASA, which is about all I teach in my Intro to AI course, right? So this is about the level of my knowledge. of how this works. But basically, you've got a sound where you're mixing it with, the way that they test this is which isn't right. Yes, I know, Lombard effect and all that. Okay, fine. Sweep it under the carpet. So you've got some speech and you've got some noise. You mix it and you've got a noise. And one of the ways that people look at this problem is to try and get the speech dominant parts of the time frequency mask back out. So let me play you quickly so here's the original. This is one of those all voice sentences that the CASA folks use.
Why were you away a year, Roy?
Okay. Now I'm going to mix this with 0 dB.
Why were you away a year, Roy?
Okay, it's pretty hard to understand, right? And the idea is if I get the idealized barrier mask, I actually get back some of that speech energy.
Why were you away a year, Roy?
Okay, so that's not too bad. All right, it's not completely intelligible, but it's certainly a heck of a lot better than the noise. Okay, so what we're using is a system that a student in the lab next door had developed, where they had frequency-specific MLPs where they're trying to label 1 or 0. Okay, and then they have these heuristic and hand-tuned ways to clean up the thing. And the question is, can we build these two-dimensional CRFs? And the answer is yes, otherwise I wouldn't be telling you this, right? Okay, and so we put in a bunch of features, and we're doing kind of, we've kind of reconstructed their handcrafted system to some degree. It's not perfect yet. We're in sort of, in progress. But here is the threshold. This is just if you take the MLPs and you threshold them. This is what you get back.
Why were you away a year, Roy?
Okay, so you hear a lot of sort of burble, and that comes from all these high frequency things that are coming on up here, right? And this was the CRF. It cleaned it up.
Why were you away a year, Roy?
It's still not perfect, but it's closer to the idealized.
Why were you away a year, Roy?
Right, it's closer to the idealized binary max than the threshold in MLP. And you'll notice the things it starts to do is it starts to close in this figure here, right? Here it's pretty fragmented. It gets rid of a lot of the speckle noise. It's doing the obvious things. It's like as if you put a filter over it. So I'm not going to say magical properties and all this stuff. But it's giving us a framework to start thinking about how to integrate all these different kinds of features. Just so that you can hear what their system sounded like.
Why were you away a year?
Again, not perfect, but I think theirs sounds a little better than ours does. Yeah.
So how is the MLP used for determining the mask?
Oh, so what we do is there's a number of features that are related to the harmonicity of so one of the things that they assume is that they know the pitch, which actually they do a variant of it where they don't, but you know the pitch, so therefore you can figure out things like, what is the pitch period that's closest to this particular frequency, and how far off is it from an integer of that frequency? And you can look at the autocorrelation between channels and all sorts of other things. Okay, so there's a number of features that go into the MLP, and then looking over that window, they basically make a local decision, right? And then we're just cleaning it up with a more global decision. So it's a lot like the way that we're doing speech recognition. Okay, so why am I really interested in this in the long term is that I think there's a nice connection between this and the phonological problems that we were talking about before. I think that when you get noise masked speech, that what's coming out is actually some part of the phonetics and not a complete, you're getting some phonetic masking, and the question is, can we learn how this frequency masking and this phonetic masking happen at the same time? And that's sort of a grand challenge. And I think we'll be working on that for a while. But it's an interesting problem to think about. Okay, that's a way that phonological features might actually get us some robustness to noise. Okay. So last, basically, I give you sort of my view of why we're interested in the CRF stuff and all of the overlapping feature stuff. We're looking at it in two different problems, and I tried to be a little bit honest in this talk and say, it's not a panacea for everything. You do need to think carefully about the way that you're combining things. They tend to over-smooth the posterior space if you're doing the wrong, possibly if you're doing the wrong training criteria. You know, Ilana's work basically showed that the log linear form might not be appropriate for all feature combinations. You need to be thinking about features carefully and stuff like that. Okay, thanks a lot.
So one application of the tandem features where they used to take, people take tandem features and combine them with the original acoustic features and then give it back into, to combine both the original PLP with the tandem features and then use them for use with the SMM GMM system.
Right, yeah.
So the idea was they could correct the problems with the original acoustics and so on and so forth. So have you tried combining the original acoustic features with tandem features?
Yeah, so in fact, that's basically what it ends up doing is basically washing out the difference between the tandem and the cranium system. Both of those actually work.
So that's the combination.
So this is the combination with the original acoustic features. You know, yeah, with yes, right, yes, that's right. We add in the MFCCs again.
There was a recent paper by Herman Nye, I think, who proved that CRFs and Gaussian HMMs are actually equivalent.
They're not.
They're not. Okay.
They are under certain circumstances, actually. So.
Actually, that's right. He didn't say in all cases.
Yeah, and in fact, if you read you have to. So if you take the top level version of that, yes, they are. So here are the relationships. Basically, you have to assume that the model structure is the same. So for example, I can't say that a CRF that pays attention to transitions on acoustics is equivalent to an HMM, right?
I think you showed that if you take the parameters and the models that you compute from a CRF, you can generate an equivalent HMM.
From a particular kind of a CRF. So a linear chain CRF with only state features. That's right. That is right. You can compute the equivalent HMM. People have shown in the past the other direction, right? That you could do, that you can take the HMM parameters and make the CRFs, right? And what does it really say? I mean, what it says is that that CRF training is really a heck of a lot like MMI training for HMMs, and you know, modulo differences in implementation and stuff like that, you probably, for the same model structure, would end up with roughly equivalent things. You know, that said, usually MMI, you know, so where's it different? MMI usually starts from an ML baseline and then you adapt to an MMI, you know, criterion. The CML basically starting from flat start, right? So you're starting from different spaces, and the algorithms don't work exactly the same. But roughly speaking, if you look carefully at the criteria, they are doing roughly the same thing. So my answer to that is yes and no, right? Yeah.
Question, but let me see if there are others. Okay, can you go back to those colored pictures about the phone probabilities in time? Yeah.
Yes.
Yeah. So for either of these, how fast does this run? Assuming you could do all the optimizations that you needed to, would this run on speech, let's say, 10 times faster than real time, or 100 times faster than real time?
I couldn't tell you the difference between 10 and 100 because for me, they're you know, for the small data set that I'm looking at, it's relatively equivalent.
No, the reason I'm asking is because with phone posteriors like this, if your task was something like spoken term detection, maybe you don't even want words in the beginning.
That's a
you
good point.
Do a phone transcript.
That's true. That's true. If you're doing spoken terms.
Yeah, consistency might be more important.
Oh, the bottom one looks very good, I think.
That's why I like the bottom one.
Yeah, I
for
like
that
the bottom
reason.
one.
It would be really consistent for that kind of a task.
Right, which is essentially, I mean, it's equivalent to me saying, yeah, we need old school pronunciation modeling, right?
Uses 9-frame inputs.
Sorry?
9-frame input or something like that, right?
Yeah.
Yeah. If you use the longer input, it would start looking more like the
yeah, so in fact,
value.
Matthew's stuff where, I mean, he'd asked, actually, he and I had a conversation about Matthew Magma-Das,
Yes.
is that how you say it? Yeah, if you look at the posteriors over like 25 frame windows or something like that, he did.
Yeah, we go all the way to like 100.
Yeah,
frames.
and tends to smooth it. And so that's an interesting question.
Starts looking much more like the bottom.
Yeah, and that doesn't surprise me, right? I think it's, yeah.
It's not to say that it's better for HMM. It's not to
No.
But
Yeah,
if
and
you are after phonic,
Matthew wanted to actually
that's actually the bottom one is better.
Yeah, Matthew actually wanted to compare the CRF to that longer time frame window that he was doing. And I keep on meaning to give him the code, and I'm working out the licensing issues. By the way, I should say, we do have a toolkit which, if I can ever get my Office of Technology and Licensing, strike that from the record, to actually give me the license. Yeah, there you go. Then maybe they can, if they watch this, they can get the message that we're going to have an open source toolkit for this that people are welcome to use. So, Jason.
So, with regard to this slide, it seems to me that there's nothing wrong with old-fashioned pronunciation modeling as long as you have enough phonemes. And you might not want to take the phone set that you're using now if the CRFs are going to be peaked, because you might lose some information about things like vowel color.
That's a good point. Yes, that's right.
But you could expand the phone set as long as you can figure out how to train when you might not have supervised data.
Yes, that's right. That's a very good idea.
The truth is, like, if you have an error like officers, I think it's not an error. It's
no. I think the CRF is doing the right thing.
It's not the error of a machine, and you shouldn't try to fix it. Basically, the machine shouldn't try to fix it.
Well, the question now becomes, I'm pushing off the problem now to the lexical model.
That's what people count.
Right.
They count it as an error, but it's not an error.
Yeah. Well, it's right. I mean, so we're now pushing the problem off the lexical model, which now means that I'm back to year one of graduate school, right? In that we're back to doing the sort of how do I model the relationships of words to phones, of these phone observations now to words. And one of the things that we're looking into actually is to think about these phone observations that we sort of compute now as new sort of bits of evidence towards words. And the question is, what's the right framework to think about partial evidence of words in terms of word decoding,
Jensen is saying, I think, is very much right, and you will be probably first one to agree. If we know what people are saying, they will help us greatly because they are not making errors without the reason.
Yes.
Like for and were. I mean, it's
that's right. I mean,
just some parts of the country, I guess this is normal.
Yeah, and in fact, so the reason why we're allowed to do that is because there's enough information to get the word officer back out no matter what. And this is one of the.
That's bad because we never learn basically that people say other things.
Yeah.
Because you often don't see it as the output because the system fixes it.
Yeah. Right.
So the point that you made at the end was, though you decrease the you increase the phone accuracy, you couldn't be able to increase the word accuracy because there were so many pronunciation variations, right?
That is a guess. That is not a. We haven't gone through and marked like what the. I mean, we can mark the phone accuracy.
Pronunciations that don't match his pronunciation lexicon. That may be more.
That's the way that I would phrase it.
Given the way this is playing out, you may actually have fewer pronunciations.
So have you done any type of measurement on the correlation between the errors that you are making and the HMM models for the phone accuracy and stuff?
Yeah, not yet. That's on the top of the document.
You are losing on some part of the data, which is more important for the word accuracy, but you are gaining that, I mean, in the other part, but overall the phone accuracy is better.
Yeah.
But it's not helping the word.
But
I mean, because to me, like the officer, versus officer, even if it was pronounced as officer, but it's going to be replaced by officer, the word officer when you are doing the word recognition, right?
Yeah.
Because, it will be replaced by the closest match.
But then my point is the system is actually to be blamed.
Yeah, that's true.
We see this over and over. This picture is actually very nice. We've seen it many times. You get much better phoneme string, and HMM likes the fuzzier representation because it likes to fix things the way it thinks it should be.
That's right.
Because of the top-down, because of the allowed pronunciations, and so it happily fixes verb for fur if you give it fuzzy representation. Yeah. But the truth is that out there is verb. Right. You can't help it. It is a verb.
That's right.
And people, you can't correct people, right? I mean, that's what they say.
Well,
so you would
we can,
you better know, or you put it as into pronunciation model, then you see it often.
Yeah. I mean, we can, but they get upset when we do, right? So.
Sure, people get
but,
right now, I mean, you know.
But no, seriously, yeah. And that's why I think that what this really says is that we need to think about new ways of thinking about lexical models, right? That's
think about new ways to do speech recognition.
Well, yeah.
That's what I always say. Serious.
Hinek, you should write a paper about that. But seriously, yeah. I mean, I think this is so one of the things that I take home from all of this is that it's nice that it's certain, and the question is one question that I haven't answered with this question is, with these things is it certain and discriminable from other things, right? So I don't want to make grand claims about like this is better than this because I don't know that there's enough discriminable information. Like let's imagine that all of the words basically came out looking exactly the same, then I'm not doing myself any good, right? The real question is how much information. I don't believe it's happening, but I can't say that it isn't, right? Okay, so I'm being very careful because I could prove myself wrong later.
If you just put your coding labels there next to these things, maybe you could probably tell quite a bit.
Yeah, and you can do decoding things, and yeah, I mean this is like what my student did last week kind of thing, right? So that's clearly, yeah, hot off the press kind of thing. But yeah, the real question is what.
Analysis is really going to be very important.
Sorry, what?
I'd like to see more analysis actually.
Yeah. Yeah, I'm just sort of scraping the surface of the analysis that we did, but and again, in a 4-page interspeech paper, if you can't do that either. That's why God invented journal articles, right? So that is certainly a place that we're going to be looking and thinking about. Do we get enough information out of this CRF to actually, carry on? Maybe we need to think more about changing this, or maybe we don't. I don't know. I mean, certainly it's not going to. Certainly, taking these and doing random style stuff is not going to help us, right? So if we were committed to, and which we're not necessarily, doing the random stuff, we wouldn't want to do this anymore, right? We want something that looks more like that, right? Just because of the Gaussian nature. Okay. Thanks for having me.